Hello, everyone. So I'll be discussing lab exercise 2, which is exploring Haskell. I'll just be discussing how you would answer this lab right here. So if ever you're not using the GHC compiler that I've sent in the course pack, for example, you can use Haskell in your browser using REPL. You need to include this snippet of code right here. But if you are using the GHC compiler that I provided to you, then you can't ignore this one right here. So what you're gonna be doing for this lab exercise, you're gonna be creating a Haskell file or a .hs file. What it's going to look like is something like this trying things.hs file that you've seen me demo. This one right here, for example, it's just a list of all of the functions that you have created. So all of the functions for this lab exercise will be placed inside this HS file right here. So for example, this one right here contains the functions successor, predecessor, apply twice, add three, blah, 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 and so on. So what are the functions you're gonna make? They're divided into three categories: easy functions, recursive functions, and higher order functions. So easy functions, they're pretty straightforward. The cube function, for example, consumes an integer and produces the cube of that integer. I sometimes use this terminology right here, consume and then produce, because the terminology used for imperative programming, which is pass and then return, it's not 100% accurate for functional programming. So when I say produce, I basically mean it accepts these as parameters. And when I say when I say produce, it means it returns this specific value right here. And when I say consume, it accepts these values as parameters. Okay. So for the simple functions, you have the cube function, for example, which is used like this. So cube 3, for example, would be 3 times 3 times 3, which is 27. The double function would just be simple as well. Double 5 would give you 10. So those are simple to write functions. The functions I haven't discussed so far are these recursive functions. But you have heard of recursive functions in your COMSA 11 and COMSA 21, so you just have to translate those functions into Haskell. So try to experiment as well while you're doing this lab exercise, and uh, you can create interesting results and you can learn how Haskell works by doing. So the first function is just the modulus function, which consumes two integers, x and m, and produces x modulo m. So if you have this application, modulus 3 and then 6, for example, the remainder will automatically be 3. If you have 6 and 3, for example, you could expect that the remainder would be 0. Something like 17, 3, for example, would give you 2. The remainder is 2. There are libraries in Haskell that contain the modulo operator. I think it's actually built in anyway, but do not use that built-in modulo operator or modulo function. You have to create your own using recursion. Factorial is very simple. It consumes an integer and produces the factorial of that integer. So factorial of the integer, oh, that's too big. 3, for example, is 1 times 2 times 3. So that should give you a 6. Factorial of 4 is 6 times 4, which should give you a 24. The factorial of 10 would be something big like that. So I've shown an example right here, which is the summation function, which consumes a natural number and produces the summation of the numbers from 1 to n. So I've given you the answer for this one, just to sort of discuss how I created this answer so that you have an idea on how to create these recursive functions as well. So as much as possible, create these type annotations right here. So you would expect that the summation function would consume a natural number. Uh, in that case, our a best type for that would be int, although an int is not necessarily a natural number, but that's fine. And then it produces another int. So if you remember type annotations, right, the last type that you write in this series of arrows would be the type that this function produces or returns. The others that are to the left of the last one would be all of the values, the types of the values that it consumes or accepts. So what does the summation function do? The summation of sum x would be, oh, I'm using n in my like in my notes right there. So the summation of some natural number n would be something which is equal to, again, in Haskell, you don't use the keyword return, right? Because the line that you write here or the body of the function is automatically what you return. So for recursive functions, the three of these that you see, modulus, factorial, and summation, they have similar patterns. They have this if-else clause because uh, a fac- a recursive function must have a base case for it to end, right? So uh, what I usually do, I start with a base case. So the base case for this summation function would be if n right here would be greater than, or sorry, would be less than or equal to 0. That would be my base case. I do not have to concern myself with negative numbers right here because according to the instructions, you assume that the natural number, you're passing or you're consuming natural numbers only. So uh, the base case right here is that if n is less than or equal to 0, then what do you return? So the summation of 0 would be 0 right there. And then if it does not follow that base case, if it does not satisfy that base case, then what do you do? Then this is where you recursively call summation. Else you add the value n and add it. So add n to the summation. This is the recursive call of n minus 1 and yeah, that's just it. It only accepts one value, Raman. So be careful with Haskell's syntax right here. So if you really want to make sure that your code would be parsed in the way that you want it to be parsed, you can add these parentheses right here. So for example, the if right here must accept a Boolean man. So n is less than 0, then 0, else this specific value right here, n plus the summation of n minus 1. And if you really want to emphasize this part right here, that you're calculating summation of n minus 1 and then adding that to n, then you add that extra parentheses right here. By the way, if you're not familiar with the syntax that I'm showing you right here, this if-else syntax, you can refer to the Haskell cheat sheet that I've also shared in the course pack. So just to reiterate what this if-else does, an if-else is an expression that evaluates into something in Haskell. So this whole if-else, if-then-else clause right here evaluates into some value. What does that evaluate to? It depends on the Boolean function right here, or the Boolean expression right here. If this Boolean expression evaluates to a true, then the whole if-then-else clause will evaluate to whatever is inside the then clause. In this case, that would be 0. On the other hand, if this expression right here would evaluate into false, then the whole if-then-else expression would evaluate into whatever you put in the else clause. So that's the reason why Haskell's if-then-else clauses they're patterned like this. Every if must be followed with an else, because if the if is missing an else, then that expression is incomplete, because what does your expression evaluate into if the boolean is a false one? So you always have to provide an else clause so that your expression has an alternative. Okay, so assuming this works, the summation, I'm going to save it right here, and I'm going to load this trying things Haskell file. So this should work. Summation of 0 would be simply 0. That would be the base case. Summation of 1 would be 1 plus the summation of 0. And then finally, the summation, let's say summation of 5, for example, would be 15. So just to discuss, what is the intuition behind this one right here? If you are given this one, summation of 5, what does this expression evaluate into for Haskell? So the summation 5 right here evaluates into the else clause, right? Because 5 is not less than or equal to 0. It does not go into the base case. So for this clause, it will return false. Therefore, it should go into this, it should evaluate into the else clause. So what is the else clause? The else clause is n, which is 5 plus the summation of n minus 1. So 5 plus summation of 4 right there. Oops, I don't have to add summation of 4. So what does this summation of 4 evaluate into? So 5 plus summation of 4. Again, we'll go back to the alternative case or the else clause, since it is still not less than or equal to 0. So this will evaluate into 4. Oops. 4 plus summation of 3. This whole thing right here, summation of 3, will still go to the else clause because it is still not less than or equal to 0. So you will get 5 plus 4 plus 3 plus summation of 2. And then this one will evaluate into 5 plus 4 plus 3 plus 2 plus summation of 1. And then I'm running out of space. So this one right here would evaluate to 5 plus 4 plus 3 plus 2 plus 1 plus summation of 0 of 0. And in this case, summation of 0 will go to the base case because 0 is indeed less than or equal to 0. And if you're given a summation by 0, it will automatically evaluate into 0 in this case. So you'll end up with 5 plus 4 plus 3 plus 2 plus 1 plus 0, which is indeed 15, which is why we got this answer 15 right here. Great. Okay, so moving on. We have the last category right here. These are a bit challenging. So this is the compose function. So this is a higher order function because this function accepts two functions, and at the same time it also returns functions as well. You notice that with the type signature that you see, it returns an int to int, but it also accepts two int to int functions as well. Okay. Command Shift 7 1. There you go. How do you use this? So you use the, wait, let me reload the file which contains the answers to this lab exercise. Hopefully I don't accidentally share this to you. There you go. Just to clear out all of the clutter in my PowerShell. So to use this, you just apply the function compose with other either functions or lambdas. So we already have the functions double and cube prepared, and both of these functions are int-to-int functions as well. So they will be consumed, or they will be accepted by the type annotation of compose. So if you remember, this application right here, compose double cube, will return a function. So if you just press enter for this expression right here, you can expect that this would return an error because, again, Haskell is trying to print a function and it does not know how to print it, therefore it's complaining. So the way you use this is you can either bind this to some name, for example, C. So the error would not appear anymore, and you can use C as the composition of the double function. So the composition of double cube would be the double of the cube of a number. For example, 3 or 2. Let's write 2. So the double of the cube of 2. Meaning, first, what is the cube of 2? That would be 8. So what is the double of 8? That would be 16. So you would expect the answer to be 16. Now this answer would be different if you try to, let's bind it to another identifier. D is equal to compose cube double, for example. Since composition is not necessarily commutative, so this could give you a different answer if I use D and then 2. So this is the cube of the double of 2. So first you double 2, giving you a 4, and then cube that value. So cube of 4 is 64. Amazing. And you don't have to bind the function that is produced by compose. You can use it anonymously like this: compose cube double and then 2, like that. You can even again remove this because Haskell will implicitly associate the function applications from the left. So compose cube double 2 will still give you the answer 64. And then the next higher order function you need to implement is very simple. It's just subtract maker. So it consumes an x and produces a function that consumes an integer and produces x minus y. This is actually incorrect. Let me rewrite this one. What it should produce should be y minus x. There you go. That makes sense. Okay, so how do you use it? So for example, you create a subtract maker, or you apply subtract maker to an integer right here. So this expression right here is similar to subtract 3. So if you apply this to another integer, so 2 minus 3 should give you negative 1. Subtract maker 4 would be 4 minus 3, so 1. Subtract maker 1 and then 0 should be negative 1 as well. Again, what I'm doing right here is I'm using it anonymously. You can also bind this with an identifier named -1, for example, just to demonstrate its usage. There you go. The challenging one right here would be the higher order function called apply n times, because this is both a higher order function and at the same time a recursive function as well. So this is sort of the challenge part of this lab exercise. Just try it out, just try things, and yeah, try to answer this one. The idea here is that if you're given based on the type signature right here, first, it consumes a function of int to int variety. It consumes another integer and then another integer and produces an integer itself. So what it does is this function right here, it's gonna apply that n times. So for example, I think this would be illustrated with an example the best. So apply n times the function double. How many times do I want to apply it? So for example, if I want this to be applied 2 times to 4, I should get 4. So double of 4. So again, this should be similar to of double of 4. So I'm getting 16. That's the same answer. So that is applying double twice. If I want to apply double 3 times, right here, then I'm getting 32 because what I'm doing is similar to applying double thrice, like this expression right here, 32 as well. Okay? And again, this would accept any named function or any anonymous function. So if I create a successor function right here, anonymously using a lambda, so y becomes y plus 1 right here. If I apply this 3 times to the number 4, so the successor of the successor of the successor of 4, which should be 7. Okay? Yeah, so this is the challenging part. Try to answer this last so that you have a little bit of experience on how to create both recursive functions and anonymous functions. Sorry, higher order functions. Because again, apply n times is a combination of those two. And that's all. Don't hesitate to reach out to me if you have any concerns about this lab exercise right here or any lab exercise for that matter. And I will help you in any way that I can. Thank you, everyone.